Hey everyone. In this video, I'm going to explain the difference between frequentist maximum likelihood estimation and Bayesian posterior sampling in the context of linear regression. Okay? And to kind of get started, I want to go back to the example that I used to introduce the idea of maximum likelihood estimation last week. And particularly, we looked at this kind of trivial example of estimating the probability of a woman being appointed to the US Supreme Court. And we started our argument based on the discussion that ultimately we're interested in the probability distribution of theta, which is the true probability of a woman being appointed to the Supreme Court, conditional on y, conditional on the data that we observe. And the problem is that we cannot directly compute this probability p of theta given y. Okay? On the other hand, what we can do is we can compute the probability of observing a certain set of Supreme Court justices under kind of conditional on an assumed value for theta, right? So the kind of the probability of y conditional on theta, that is something that we can compute if we're willing to assume a given a certain probability model. Okay, and kind of the idea of likelihood or the likelihood of theta of a certain parameter value conditional on y is that this likelihood of theta, the likelihood of a certain parameter having generated our data y that we observe, is proportional to the probabilities, to the inverse probabilities of observing a certain set of data conditional on theta. Okay. So in this specific example of the US Supreme Court, we kind of had to make a couple of kind of simplifying assumptions to derive this likelihood function. Okay, we have to assume a probability model, and the assumptions about this underlying probability model ultimately kind of have important implications as to how we kind of conceptualize the underlying data generating process, right? So here we basically kind of think of selection of US Supreme Court justices as a set of Bernoulli trials, so just a dichotomous choice between a man and a woman that could be appointed. Each individual choice is independent, each individual appointment is independent of previous appointments, and we also assume that the kind of underlying true probability of being appointed or of a woman being appointed versus a man being appointed is constant over time. Okay, so in that sense, we kind of model this problem as a set of independent Bernoulli trials. Okay, so that means the probability of each individual justice to be a woman or a man, conditional on our theta, is just a simple Bernoulli trial, which is just theta, that's the probability of the appointed justice being a woman, to the power of yn, so that is just a dichotomous indicator, which is either 0 for a man and 1 for a woman, times 1 minus theta to the power of 1 minus yn. So in other words, for every woman that is appointed to the Supreme Court, we have the probability of theta. For every man, we have, and 1 minus the power of 1 minus yn for that woman, that's 1 minus 1, it drops out, so we are left with theta. And for every man, it's 1 minus theta, so 1 minus the probability of appointing a woman. Okay, so that's a simple Bernoulli trial. And in order to get the overall likelihood of the data that we observe, which is all the justices that we see now on the Supreme Court, this is of course an older picture with Ruth Bader Ginsburg, unfortunately not on the Supreme Court anymore, and instead we have Amy Coney Barrett, but the number of women, of course, stayed the same. So the likelihood is then basically just the product of each individual probabilities of Bernoulli trials for each of the justices that we have on the bench. Okay, so essentially we're basically plugging in YNs for each individual justice and then multiplying pi to the yn times 1 minus pi to the power of 1 minus yn for all justices that we currently observe. Okay, and that ultimately forms our likelihood function. Okay, in this likelihood function we plug in all the data that we observe, that's all the y's, and we can basically, if we plug in different values for theta, we get different values of this likelihood. And the idea behind a maximum likelihood estimation is then to basically search for a theta value that maximizes this likelihood function. Because if we maximize this likelihood function, we ultimately find the parameter value that, given our assumptions and given our probability model and our assumed data generating process, that theta is the most likely theta to have generated the data that we actually observe. Okay, and we kind of derived not only the likelihood function, we also derived the log likelihood function, where we just take the logarithm of the original likelihood function in order to make this function ultimately computationally more tractable, because the logarithm will turn the product sign into a sum, and ultimately both numerically and analytically it'll be easier to identify the maximum based on the log likelihood function than on the likelihood based on the likelihood function. And of course, the maximum of the log likelihood function is equal to the maximum of the likelihood function. As you can see here, I plotted for this particular problem with this particular Supreme Court and the data that we observe. I plotted both the likelihood and the log likelihood function, and we can see that the maximum is, of course, at exactly the same position, which is, of course, just 1/3, because we have 3 out of 9 justices, which is, obviously a trivial problem. We have 3 out of 9 justices being women, so obviously the under the assumed probability model, the maximum likelihood estimate of the underlying probability of a woman being appointed to the Supreme Court is, of course, 1/3. Okay, so that was the basic idea to introduce kind of the concept of maximum likelihood estimation. The key is we can use exactly the same logic and exactly the same kind of framework to estimate much more complex, estimate parameters in much more complex models and much more complex more complex questions involving multiple parameters and involving all different types of assumed probability models, right? Because we just started with one probability model here, just a Bernoulli trial or a sequence of Bernoulli trials, but we can basically assume any other type of probability model and data generating process, plug in our assumed data, and then solve for the most likely parameter values or set of parameter values that have generated these data. Okay, and now the key is that we've done this in the simple bivariate OLS case. Okay, we kind of talked about how to estimate OLS using maximum likelihood estimation, and again we kind of worked with a fairly simple example forecasting the election, U.S. presidential election, from the economy, so average recent growth in personal income prior to the election, and then the dependent variable that we examined was incumbent vote share, the incumbent party's vote share in that presidential election. Okay, and that was the simple example that we kind of worked with, and we kind of derived just in the same way we did it for the simple example of Supreme Court justices, where we just had to estimate one parameter. We specified under the assumed kind of data generating process and assuming normal error terms, we kind of set up a log likelihood function for this simple linear regression problem with one predictor and one dependent, one outcome variable. But now we are not estimating just one parameter, theta, like in the previous example, we're actually estimating 3 different parameters. The 3 different parameters are both beta 0 and beta 1, which is the intercept and the slope for our predictor. That's the average recent growth in personal income. And the error variance, that's sigma squared. Okay, so in this log likelihood function, we have 2 parameters, or 2 types of parameters. One is the error variance, and one is beta, which here is a vector of intercept and slope. And we have our observed data, which is our outcome variable and our set of predictors. In our case, it's just one predictor plus a set of ones for the intercept, essentially. But of course, this would be the same for like a multivariate regression problem. Okay. And so one thing that we did is we kind of specified the same, similar to this graphic, which was quite simple, with just one probability that is bound between 0 and 1, and a fairly easy, probability model. We can, look at the log likelihood depending on different probabilities and say, okay, the most likely value is kind of about here. We can do exactly the same thing in this bivariate linear regression problem, where we have this likelihood surface now in a multidimensional space. And I kind of already simplified things a little bit because I'm ignoring sigma square here. I'm just setting sigma square to, assuming we knew the true value for sigma square. We're just looking at beta 0, the intercept, down here, and beta 1, that's the slope parameter. Okay, and so we're doing exactly the same we did previously. We're plugging in our data into our log likelihood function, and we're plugging in different values for our intercept and for our slope, and we're computing the likelihood. Okay, and we get different values for this log likelihood. And now, just as we did in the previous example, we can maximize this log likelihood function in this multidimensional kind of log likelihood surface, and find a specific point estimate for which, basically for a specific value of beta 0 and a specific value of beta 1 that maximizes this likelihood function. Okay, and if we do this, then the result is the following. This is the actual maximum likelihood estimate based on our programmed likelihood function that we discussed last week. And we see this is, of course, kind of in the center of this this contour plot. We have a intercept of around 46, 47, and a beta 1 slope of around 2, what might it be, 3, something like that, something a little bit above 2.5, probably 3 point something. And here we have an intercept of like 46, 47, okay? And it turns out that intercept and that slope is the intercept and slope of this ordinary least squares regression line, okay? So we talked about the assumptions under which basically OLS is equivalent to the ML, or OLS is an MLE, a maximum likelihood estimate, basically, of the linear regression model, okay? So basically, if we're choosing the parameter values based on maximizing this likelihood surface, or finding the peak of this likelihood surface, we basically come up with a regression line that minimizes the sum of squared residuals, and that's just this regression line. It has a intercept, as you can see here, of about 46, 47, just like we have here for beta 0, and we have a slope of around 3. So with every 1 unit increase in the average recent growth in personal income, we have about a 3 percentage point increase in incumbent parties' vote share, 3.1 or whatever it is approximately. Okay, so that's our maximum likelihood estimate in this simple linear regression framework, right? The next thing we talked about is quantifying the uncertainty around these estimates, right? And we talked about how we can basically look at the curvature around this specific point on the likelihood surface to derive the standard errors. So the uncertainty kind of measures for each parameter, right? And we talked about the Hessian matrix and information matrix, and how we can kind of transform that into a variance covariance matrix, which ultimately tells us or allows us to extract standard errors for our point estimates. Okay, and basically what this allows us to do is we're looking at the curvature around that specific maximum. We're quantifying the curvature, and based on that curvature, we can compute the standard error. Based on the standard error, we can compute something, you know, like the 95% confidence intervals, right? So here I kind of added the 95% confidence intervals for beta 1 for the I should say here, this is for beta 1, the 95% confidence interval for the slope, as well as the 95% confidence interval for the intercept, and kind of translating this uncertainty around the slope and the uncertainty around the intercept into kind of our scatter plot. We can kind of add this 95% confidence interval around our linear prediction as a function of the average recent growth in personal income. Okay, so based on the curvature on this likelihood surface, we can derive the standard errors of each of our parameters, and based on that, we can then kind of add confidence intervals for our predicted regression line. Okay, so that was kind of all logic within the maximum likelihood or classic, you know, frequentist inference maximum likelihood framework, which of course, if we assume normally distributed errors, kind of is equivalent to the OLS minimized sum of squared residuals. Okay. Now, how is posterior sampling different, and why do we want to use STAN instead of just running LM and just running basic linear regression, and or how does kind of posterior sampling work in this context, right? And the key point here is that posterior sampling is not, you know, if you're following me onto this point, posterior sampling is not that, you know, different. The only difference is that rather than kind of finding this point, you know, that maximizes this likelihood surface, and then examining the curvature around that point to kind of get uncertainty estimates around our parameters, what we're doing with posterior sampling is we're taking the surface and we're taking random samples from that surface. So we're taking random samples, and each random sample is basically a specific value for beta 0 and a specific value for beta 1 and any additional parameters that we have, right? So rather than maximizing this surface and finding the point for which this likelihood function is maximized, you can think of it as taking a similar plane. It's not exactly the likelihood because it's a posterior distribution, and we'll come to why it's different from the likelihood. But it's, at least if we're assuming kind of completely flat non-informative priors, then the posterior distribution converges to the likelihood. Okay, so then what we do is, rather than maximizing that plane, that posterior distribution, we're just taking random draws from it, where basically the probability of taking a draw from a specific point is proportional to the actual density or the likelihood value, essentially. Okay, so in other words, the higher the likelihood, the higher the probability that we take a random draw from that specific point, right? And you can see here, this is now 4,000 draws from our basic stan GLM linear model with the same data. We're taking 4,000 draws in this case, and each of those draws is one specific beta 0 value and one specific beta 1 value. Okay, and basically the probability of where each draw is taken from is proportional to these likelihood values that we computed previously. Okay, I'm glossing over some details because it's not as I mentioned, it's not exactly the likelihood function, it's the posterior distribution, but we'll talk about exactly how they're different in the upcoming videos, right? The point is that rather than maximizing, we're now taking samples, okay? And so rather than having one regression line for one specific maximum of the likelihood surface, we now have 4,000 possible parameter estimates for our intercept and our slope. And we can basically, each of those 4,000 draws, we can draw a separate line for each of those different draws, right? And so in this graphic, in this plot on the left, I now basically included 4,000 different regression lines, which were all drawn from this posterior distribution, okay? Now, why are 4,000 regression lines better than one regression line? Well, the point is we can still use all those simulations to get our point estimate. We can just look at the median of all those simulation draws and we get our point estimate just the same as we had our point estimate in kind of the classic frequentist OLS framework. But we can also directly use these simulation draws to quantify the uncertainty around our estimates, right? So rather than having to look at the curvature around the maximum likelihood estimate and kind of relying on the central limit theorem to kind of assume basically normality around that point, we can directly rely on our posterior samples to quantify the uncertainty, okay? So we can basically just look at 95% credibility intervals of our parameter estimates based on kind of the quantiles in our posterior draws, okay? So this set of simulations directly allows us to quantify the uncertainty and then also to propagate that uncertainty in prediction. And that's going to be kind of the topic for the next video, okay? So you see how they're clearly related, kind of OLS from the maximum likelihood perspective, kind of sets up this likelihood surface, maximizes it, finds the values that are most likely to have generated the data. And then we kind of derive uncertainty around that. In posterior sampling, we take random draws for different parameter values, but also assuming the underlying probability model, assuming the underlying data generating process. And here each random draw is kind of, the likelihood of each random draw is proportional to the likelihood of that specific parameter value or set of parameter values having generated our data. And so we get a set of 4,000 draws, which all kind of imply essentially different regression lines through our data. And we can then summarize these simulation draws to get our point estimates, and we directly have we can directly quantify the uncertainty, okay? So basically going back to why use LM versus STAN GLM, of course in a lot of cases, particularly when you have large data sets with and no clear prior information, LM, the basic linear regression command in R, and STAN will give you ultimately the same results, right? Even in our bread and peas model that we looked at here, the intercept and slope for our basic linear regression is essentially equivalent to the intercept and slope that we estimate using STAN, right? The important difference is, one, that this is not a maximum, this is not kind of based on maximizing the likelihood function or minimizing just the sum of squared residuals, but rather we're taking posterior samples, we're taking samples from that posterior distribution that characterizes both the data and the model, and use that to kind of summarize the parameter estimates, okay? We have, if we look at the summary of the STAN model, we have a couple of additional pieces of information. We basically have our estimates, we have our credibility intervals around or for those estimates. We have some additional information that we're going to look at regarding kind of fit and so on in the upcoming weeks and in our Q&A session. But the key point is that ultimately having the set of simulation draws from the posterior distribution allows us to kind of directly, in a very streamlined way, create predictions based on our fitted models, and importantly, kind of propagate the uncertainty around our predictions. And so in the next video, I'm going to talk about how we do that. Stick around.